This is the second of two videos on colligative properties. In the first video we looked specifically at vapor pressure lowering and why that occurs. In this video, in this video we're going to look at two other colligative properties: freezing point depression and boiling point elevation. You can see our learning targets up here. Going to ask ourselves how boiling and freezing points are affected by solutes. We want to be able to calculate these boiling and freezing points, and finally we also want to determine the molar mass of an unknown using some of this data. Alright, key ideas and definitions here. We're just going to start by explaining how freezing points and boiling points are affected by the addition of solutes to solvents. And we'll start with boiling points. Now, one thing we need to keep in mind and have an understanding of to know how boiling points are affected is what is it that causes a liquid to boil whenever it's just a liquid and it's not a solvent. Well, I'm just going to sketch a little graph here, and on the vertical axis I'm going to put vapor pressure. I'll just label that capital P, and on the x-axis here I'm going to label temperature T. Okay, and let's say we have some liquid, and I'm just going to go ahead and draw a curve, something like this. A liquid will boil whenever its vapor pressure is equal to atmospheric pressure. So let's say this point right here, we'll look at right here, let's say that point right there, let's say that is atmospheric pressure. Atmospheric pressure. Just going to follow that mark over to our graph here, and then down to the temperature scale. So for this liquid, whatever this liquid is, this temperature right here, that is the boiling point, which I will label TBP, the boiling point temperature of that liquid. Now, if we do something to lower the vapor pressure, and recall from our last video, we said if we add a solute that the vapor pressure is going to go down. If I lower the vapor pressure, then this boiling point temperature has to change. So say I've added a solute, and my new graph looks like this, where I have a lower vapor pressure. Okay, so this is the pure liquid here, and this is with solute here, and I can see that my vapor pressure is lower at every temperature. So in order to get this to boil, I'm going to have to extend this line a little further. I'm going to have to get it to a higher temperature, and I've run out of room here on my graph. So here is my new boiling point, and I can see that it's gone up. That's why we call it boiling point elevation. We have to get it to a higher temperature in order to get that vapor pressure to increase. Now, as far as how much it will increase, there is a quantitative relationship. The difference, or the change in the boiling point, delta TBP, is equal to the molality of the solution, lowercase m, times a constant, the boiling point elevation constant. I'll just go ahead and describe what each of these are. So delta TBP, this is the change in boiling point, so how much it's going to go up by. M, that is the molality of the solution. Recall also from our last video that molality is based on number of particles. So if you have an electrolyte that's going to give you more particles than you put in, you must account for that. And then finally this constant, this KBP, this is the boiling point elevation constant. And the fact that it's a constant should tell you right away that it's not something you need to memorize. You'd look it up. Every liquid has its own unique boiling point elevation constant that you'd either be given or you have some sort of table you could look it up in. Alright, so that's boiling point. We'll get to using this equation here in a second. Now, freezing point. Let's think about what would happen to the freezing point of a liquid if we added a solute. If something's going to freeze, let's just talk about water. Say we had a container of water, and I'm not really going to draw a container. Let's just say these are water molecules that are in the liquid phase. recall that when something is a solid, when something freezes, it's going to have a very orderly pattern in its particle arrangement. And with water, that comes from hydrogen bonding. So here it is as a liquid. I'll just label this liquid here. Okay, if we're going to freeze it, we're going to have to remove heat energy. You're going to have to cool it down in order to slow these particles down so that those hydrogen bonds can become rigid. And what's going to happen then is we're going to have a very standard repeating arrangement. Just going to start drawing a nice repeating arrangement here of these water molecules that we now have that are frozen, and they're all held together by these fairly rigid hydrogen bonds. I'm just demonstrating that with some dotted lines here. Something like this. Okay, so here's our solid. Now if I were to add a solute to this, add some foreign particle, if you will. I'm going to just sketch my liquid again. Here's my liquid. But I'm going to introduce to the liquid some foreign particles. I'll fill these dots in. Okay, say I had some particle that was bigger than water. Okay, here are our solute particles that are now in the solution with water. Do you think that we're going to have to increase or decrease the temperature from the normal boiling point in order to get this to freeze? Well, the fact that all these particles are in the way means that we're going to have to decrease the temperature even more in order to get this arrangement to happen. Oh, I just noticed I missed a line there. There we go. So in order to get this to freeze, I'm just going to go ahead and draw my pattern again here with the water molecules. Something like this here. Now I'm also going to introduce these solute particles in there as well. In order to get this to happen with these additional particles in there, we're going to have to lower the temperature even more, because now these interactions between the water molecules get interrupted. And it's not as easy for this to happen. So in order to get these to freeze, get these molecules to freeze, we have to lower the temperature even more. The equation, for as far as figuring out how much it has to go down, is the exact same as the one we had for boiling point. So the change in temperature of the freezing point is equal to the molality of the solution times the freezing point depression constant. So all these symbols mean the exact same thing. We just substitute freezing point for boiling point. That's all we do. Okay? So here we have boiling point elevation. That's this side. And over here we have freezing point depression. Freezing point depression. Before we go to the examples here, just want to point out this video that I've found on Khan Academy. I think it does a really good job of explaining these probably a little better than I've done. The diagrams might be a little easier to follow. So I'd check that out if this is confusing to you in any way whatsoever. All right, let's look at the example problems here. First one, it says you dissolve 27.34 grams of sodium chloride in 750 milliliters of water. What is the boiling point of the solution? The boiling point elevation constant for water is 0.512 degrees Celsius per mol. So we've added a solute to water. We know that is going to cause the boiling point to go up. We want to know how much it goes up by and then what that will cause the boiling point to be. Well, I know that the change in boiling point of our solution, this is just the equation from above up here, is equal to the molality of the solution times the boiling point elevation constant of the solvent. So I need to calculate the molality of this solution. All right. So remember, this has been a few days since we've done this. Molality is moles of solute per kilogram of solvent. So just starting with our 27.34 grams of sodium chloride, 750 milliliters of water. You might be thinking, well, geez, that's not a mass. I need to know what the mass is. Well, recall that the density of water is 1 gram per milliliter. So that would be 750 grams, or 0.750 kilograms is what that would be. All right, so from here I can just do a gram to mole conversion. The molar mass of sodium chloride is 58.44 grams NaCl per mole NaCl. Recall as well that this sodium chloride is going to dissociate. We're going to get 2 moles of particles for every mole of NaCl. We must account for that. All right, you do all this, and this should give you 1.247 mole. So I should get there. Notice the boiling point elevation constant is given to us, so at this point I can simply use this equation. So the molality of 1.247 molal times the elevation constant of 0.512 degrees Celsius per molal. Notice your units here. The molal units will cancel. We're left with degrees Celsius, which should be the case, as I want to know how much the temperature is changing by, so our units match that. This gives you a value of 0.638 degrees Celsius, which is the change in boiling point of the solution. This is not the answer. I need to consider what the boiling point of pure water is. Well, we know that the boiling point of pure water is exactly 100 degrees Celsius, so 100.000 degrees Celsius, plus that change that it went up by. This gives you a boiling point of 100.638 degrees Celsius. And there's our answer. Boiling point elevation. All right, the next example deals with freezing point depression. Recall it's the same math, though, the same equation. We're told that the normal freezing point of chloroform is negative 63.5 degrees Celsius. If 16.7 grams of ethanol, there's a formula, are dissolved in 150